Hello and welcome to the 7th video of the MECH 20 video series. Today we'll be covering a conservation of linear momentum problem. So just to start, momentum is something you'll use when the forces are too difficult to calculate, right? If you have an impact, that's a dead giveaway that you need to use something like momentum somehow, right? Either it's like impact or principle of momentum or conservation. So when do you use principle versus conservation? Principle you would use, let's say if you have time involved. Whenever you have time and velocity with forces involved, you know you're supposed to use linear, a principle of momentum. But here we have no outside forces, right? And we have no talk of time, so we're going to use conservation. So let's get started with the problem. Block A has a mass of 5 kilograms and is placed on the smooth triangular block. Smooth is important here as well. Triangular block B having a mass of 30 kilograms. If the system is released from rest, determine the distance B moves from point O when A reaches the bottom. Neglect the size of block A. Alright, so here we know that MA is equal to 5 kilograms and MB is equal to 30 kilograms. And we want the distance B moves from point O. Alright, so since we have no outside forces, we know that momentum is conserved, right? And linear momentum is conserved. And how do I know that I have to use momentum in this problem? It's because as this block falls down, as block A slides down to the left, it's going to push block B to the right, right? And I think we all can intuitively kind of understand that. So let's get started with the analysis. So the first thing I'm going to do is look at the conservation of linear momentum. And specifically, I'm going to look in the x direction, right? Because momentum is conserved in the x, y, and z directions. But here I know that B is only going to move to the right. So I'm going to just take the x direction. Alright, so we know that we start from rest. So here it's just going to be 0. And on our right hand side, we're going to have the mass of block B times VB. And then minus 5, the mass of block A, VA in the x direction. For VB, I won't even put x because we know it's only going to move to the right. Alright, and just rearranging to the other side, I get VAX is equal to 6VB. Perfect. So now we need to relate the velocity somehow. And a lot of time in these linear momentum problems, you're going to need to use relative motion. So to relate the velocities, I know my equation is VB is equal to VA plus VB with respect to A, right? And I know that VA here, it's going to go to the left, right? And that's a negative. So I have VB is equal to negative, and I'll put the x subscript here because we're only looking at the x direction, plus VB with respect to A, all right? And this is also in the x direction. So now I could substitute the 6VB I got from step 1. I can plug in the VAX in my second equation, and I get VB is equal to negative 6VB plus VB with respect to A in the x direction. And solving for VP with respect to A in the x direction, I get is equal to 7VB. So remember how in those cable problems we had S and we derived and we got the velocity and we derived again to get the acceleration? Well, here we're going to integrate to go back to get the distance because the question asks to determine the distance B moves. Alright, so I'm gonna make a note here. Integrate. So I'll call this step 3 here. So after you integrate, I get that SB with respect to A in the x direction is equal to 7SB. Alright, but this isn't enough for us to solve our problem because we're looking for SB. So we need to find out what SB with respect to A is. We're given that the length of B in the horizontal direction is 0.5 meters. And we know that A is going to travel 0.5 meters in the x direction relative to B. So that just means SB with respect to A is 0.5 meters. So that's going to help us to solve for SB, right? So SB with respect to A in the x direction. Oh, by the way, this is also in the x direction. Is equal to so we have 7SB is equal to 0.5. That gives me that SB is equal to 0.5 over 7, which is just 0.0714 meters. And that's our answer. So just a little bit of a recap. Here we used conservation of linear momentum just in the x direction because there were no forces and I made the assumption that B is only going to travel to the right, and we needed to use a relative motion here, which you need to do for quite a few of these momentum problems. And finally, another tricky part was realizing that you had to integrate and that SB with respect to A in the x direction is actually just 0.5 meters. So I hope that was clear. See you in the next one.